Alright, number 18. In this problem, we have a block being held up in the air at rest and being dropped down onto a vertical spring, looking something like this. And it's a height above the relaxed position of the spring, delta H O, H initial. The spring stretches a distance delta Y. It has a spring constant K, and that's all we have. So the mass is 700 grams, which we'll quickly convert. 0.7 kilograms. K equals 400 newtons per meter, and delta Y equals 19 centimeters, which will quickly convert to 0.19 meters. Part A. How much work is done by the block on the spring? Well, the work done by the block on the spring is going to be the same as the work done by the spring on the block, which is part B. And in fact, due to Newton's third law, they're equal and opposite. The spring pushes up, yet is displaced down. So the spring will do negative work. The work done on the spring by the block is positive because the block pushes down, the spring goes down. They're in the same direction. So the work done by the block on the spring is, again, equal and opposite. So we'll just use the expression for work due to a spring. 1/2 kx squared, and in this case our x is going to be delta y, so just to be consistent, k delta y squared, which is 1/2 times 400 times 0.19 squared, and that equals 7.22 joules. Again, positive because positive work is being done. Both the force and the displacement are in the same direction. Spring, the work done by the spring is 1/2 k delta y squared. Same, but we're going to make it negative. Because it is negative work. Alright, part C. What is the value of H naught? H initial, this, right? This here, from here to the relaxed part of it. Well, we're going to finally bring in some conservation of energy. We know that when it's up here, it has no kinetic energy because it's at rest. There's no spring potential because it's not connected to a compressed or stretched spring. So the only energy in it right now is gravitational potential energy because it has the potential to fall. So initially it's got well, yeah, let me potential energy due to gravity, and that's just mgh not, and wait a second here. Oh, yes. So we don't know anything else at h naught. We don't know the speed here. The only way to find h naught directly through h naught is if we knew the speed here and we could calculate the kinetic energy, because we knew that the potential energy up here all turns into kinetic energy by the time it hits here. So without knowing the speed here, we have to go farther. What we do know, though, is that the spring is compressed and it comes to rest. So once once a block has pushed the spring all the way down to delta y and it stopped, we know there's no kinetic energy here. We know this is as low as we can go, so there's no more. We could say there's no more gravitational potential energy. In other words, we could define zero gravitational potential energy as here. And so all of the energy is now spring potential energy. And we know what that spring potential energy is because we know how much work the block did on the spring to give it that, or how much work the spring has done to store that energy in the spring. And so we could say that the potential energy up here equals, the gravitational potential energy up here equals the spring potential energy down here. And so mgh naught plus delta y. That was a little off because we didn't know enough information here at this transition point. That's going to equal the 7.22 joules of energy stored in the spring. And we also know m is 0.7. We know g is 9.8. We know that we're looking for h naught, but we know delta y is 0.19 meters. And that equals 7.22. Solve for h naught with a little bit of algebraics, and you get uh, 0.86 meters. So that you're going to use that a lot, where gravitational potential energy will continue to decrease while spring potential energy is increasing. So let's just summarize real quick. You got gravitational potential energy only up here, gravitational turning into only kinetic energy. So we got both UG and KE, decreasing UG, increasing KE, and that continues right until here. Then the spring starts to push up, but we still are decreasing gravitational potential all the way down. We're increasing spring potential, and eventually the kinetic energy is going to reach zero here because it comes to a stop. I won't go into it, but there will be a problem. Actually I will go into it because you'll have to do a problem like this. Like where is the kinetic energy? Does the kinetic energy immediately start decreasing once it hits the spring here? Actually no, because when it first hits the spring force is zero, and when it compresses the spring just a tiny bit, the spring force is tiny, so gravity is still winning, and that means the net force is still down because, let's draw a free body diagram here. You got Fg and a tiny F spring going up. The net force is still down all the way until F spring equals Fg. That point where they're equal is where the kinetic energy is maximized. Then after that, spring force becomes larger, and then it starts to slow down. Now this problem didn't ask that, but I definitely wanted to discuss that here. Yeah, because I don't do any other sample problems where that's the case. And then part D is asking if the block were released from height 2h naught above the spring, what would the maximum compression of the spring be? So again, conservation energy, the gravitational potential energy is going to equal the work, spring potential energy. And so let's write that. That's going to be mg. Now it's 2h naught, twice h naught plus delta y is going to equal 1/2 k delta y squared. This delta y is going to be a new delta y, different from 0.19. It should be larger if we dropped it from a higher height, right? Because more gravitational potential equals more spring potential and a farther stretch, or compression I should say. Alright, stick them in. 0.7 for the mass, 9.8 0.8, 2 times 0.86, which we just found in part C. That's nice. Plus delta y equals 1/2. Spring constant is 400 times delta y squared. Ew, quadratic. Gross. So use the quadratic formula to solve for y, and you should get delta y equals 0.261 meters. You'll get a negative answer too, but that doesn't make any sense, so we'll just pick the positive one. There's 2 roots, 2 answers for this, and there you go.